So this is part 2 of the Power Analyser project, and in this video I'll finish this project, and the final conclusion of this project is the graphical user interface, which you can see on the screen. If you haven't watched video 1 in this series, please watch that first. In that video we set up the LTC2308 ADC converter with 2 channels for our voltage and current inputs. That sampled at around 10 kilohertz, and we said we can go far higher if we want to. And then we interfaced to a pair of FFT MegaFunctions to process the time domain inputs into the frequency domain. So we're at a point now where we've established that the FFTs are working. We see that bin 10 has the 50 Hz fundamental, and bins 20, 30, 40 and so on have the harmonics of 100, 150, 200 Hz, etc. So we want to push things forward a bit today. So what we'll do today is use the Codec algorithm to convert the rectangular outputs from the FFT into polar form, so we can work out the phase difference between the voltage and current, which is really important in power system analysis. We will then go on to the next important job, sending that information out of the FPGA into Matlab. And remember, our plan is to use a memory mapped master to write the data, so fundamental, harmonics, etc., into the memory scope of the embedded processor. And then basically we can printf this data over a serial connection into Matlab and our graphical user interface. So our starting point, today we have our complex outputs from the FFT. So this is DC, 5 Hz, 10 Hz, all the way up to the sampling frequency of around 10 kilohertz. Now, the reason our resolution is 5 Hz, and by the way, this is critical, is because we need our frequency bins to fall exactly on 50 Hz, 100 Hz, 150 Hz, and so on. So because we chose a 2048 point FFT and to be more specific, a 10.24 kilohertz sampling rate, each frequency bin will be at 5 Hz. So this is an example of where you have to be really careful about what your design parameters are when you design a system like this. Now, I just want to address a potential area of confusion. Now, we know that the output of the FFT is complex, so it has a real and imaginary part. But in the context of our system, what does this actually mean? Well, let's look at a signal in the FFT window. The FFT will convert this into a magnitude and a phase. Now, it's easy to visualize this with a circle. Now, the magnitude of the wave is the length of the arrow, okay, or the phasor. And the phase of this phasor, as it appears in the window, is the angle, and that angle is the phase of our signal relative to the FFT sampling window. So you can see as the signal is offset within the window, the phase of the signal changes. So this gives us a way for the FFT to tell us what the phase is relative to the sampling window. Now, taking this a step further, instead of showing this as a magnitude and a phase, we can also show this in rectangular format. So, instead of the phasor being represented by the magnitude and the phase, we can actually show it as the real and imaginary components. So our FFT actually gives us the result in this rectangular format. So it doesn't give us the result as a magnitude and a phase, it gives us the result as a real and imaginary component. But it's really important that we understand that this corresponds to a magnitude and phase. And looking at the circle here, it's easy to see how to convert from one to the other. Now, it is actually easier for us to be in polar notation. So, when we have the magnitude and the phase. So a really efficient way for us to convert to this is to use the Codec algorithm. Now, this will take a real and imaginary input and convert it to the phase. Now, it's actually not an easy thing to do. So the Codec algorithm, I think, is probably the most efficient way of doing this in hardware, and that's why it's used all the time in this kind of application. So this is why, when we look at my system, I'm using two CORDIC blocks, one of them for the voltage channel and one of them for the current channel. And this is a really nice way to get the phase. Now, as an aside, we could actually find the phase of all the harmonic components if we wanted as well. And the hardware actually gives this to us. But I'm not sure how useful this would be, so I'll only export to the graphical user interface the phase of the voltage and the current. And remember, the power factor angle is simply the phase difference between the voltage and the current. But if I send the absolute phase of the voltage and the absolute phase of the current, it's a simple find the difference calculation in the graphical user interface. So we've got all the information we need from what the FPGA is doing. So time now to go back to Quartus, and I introduced this in the first video, and we've already addressed the A to D converter code here and the timing requirements and the clock frequencies. So what we have now is a 10.24 kilohertz sampling rate. So the samples are being read into the HD converter at 10.24 kilohertz. So the FFT sampling rate is 10.24 kilohertz. It's a 2048 point FFT. There's two of them. So remember, we have two channels. One of them is for voltage and one of them is for current. They're in parallel. The sampling windows are at exactly the same time. So the phase difference will be exactly what we need to give us the power factor angle. Now, we addressed the FFT interface code in the previous video as well. That was a bit complicated, but we did get there in the end. So I think we're just about ready now to have a look at the outputs from these two FFTs and then process them a bit further. So I've just mentioned that the outputs from the FFTs are complex, so they have a real and imaginary component. So you can see here source real and source imag. They are the real and imaginary outputs from the two FFTs. Now these are 24-bit signals, okay, so they actually come in as 12 bits, but because the signal is multiplied again and again inside the FFT as it processes the data, you get bit growth. So we end up with a 24-bit signal coming out. Now, those signals are going to these blocks here, so it's basically a square and then add. So that's just an easy way to go from rectangular components to the magnitude, because Pythagoras' theorem is the square root of real squared plus imaginary squared gives you the magnitude. So that's what we're doing here. So two squares, an add, and then a square root. Now that square root is probably not necessary because that could be done in software at the graphical user interface, but I thought I'd put that in anyway. So the magnitude of the voltage and current, they appear at this point, here and here. So at this point, they are still 24-bit signals. Okay, they actually get doubled in size as you square the signal, but then they get halved in size again when we take the square root. And what I've done here is I've just made those signals a bit larger. Okay, it's not adding any new information. It's just turning them into 24-bit signals to 32-bit signals. The reason I've done this is just to make it easier to standardize the inputs into my embedded processor. So now I can keep all information going in at 32 bits. Now, just to give you a quick look at the code that's doing this, making it larger, it's just adding 8 zeros. So that works fine. Now, the crucial bit here is actually the CORDIC algorithm. And you can see, here's my two CORDIC blocks here. Okay, so one of them is for the voltage and one of them is for the current. So here we have the real and imaginary signals from all the way back to here. I've declared those as ports. So in real, in imag, real in, imag in 2. Not sure why I've used that naming convention. But that's just to tidy things up a bit so we don't have to wire them up in the graphical interface here. But basically these are the real and imaginary outputs from the FFT for the voltage here and the current here. So what I've done is I've converted those 24-bit signals down to 17 bits. I can't remember exactly why I've done that. It was something to do with a restriction on the size of the CORDIC. Okay, so I think 17 bits was the optimum size to input into the CORDIC algorithm. You can see this is the real input and this is the imaginary input to the CORDIC algorithm. You've got the clock here, and then it will quite happily output the phase corresponding to those real and imaginary inputs. They appear here, and again, I'm just converting the 20-bit signal from the CORDIC into a 32-bit signal called phase 1, and then the second one is called phase 2, and they're now ready to send through the embedded processor. And if you are playing along at home, this is inside the Codec Mega function here. You can see my input data is 17 bits and it has a fractional length of 10 bits. And the output data has 17 fractional bits and the total width is 20. So it's got 3 bits for the non-fractional parts of the signal, and of course the range that we get from this CORDIC algorithm is going to be minus pi to plus pi, so that's minus 3.14 something to plus 3.14 something. So bits 18, 19, and 20, that has to be, it has to be enough bits to encode 0 to 3, which it is. And then the fractional bits will represent the fractional part of this number. That's the bit where we want the resolution. So that's why we dedicate more bits to the fractional part of it. Now it's a bit complicated when this signal comes out of the CORDIC. It's not in 2's complement anymore. It's a little bit complicated how you convert that back to an angle in decimal in the graphical user interface. Now, I think this is outside the scope of this video, but this is something I will address in the future. But all we need to know now is this CORDIC algorithm is performing the arctan2 function. So it's good for all 4 quadrants. So it can do, and this is quite an important difference, because if you do the arctan function, it's only good for 1 quadrant, and you have to do an extra step to convert it to the full circle. But the arctan2 function does all 4 quadrants, so it doesn't matter if your rectangular and imaginary numbers are negative, which would put you into this quadrant. Whatever it is on the circle, it will give you the correct angle, and that's exactly what we want. So really the strategy now is these 20 bits out of the CORDIC, we will leave those in fixed point, and we will do the conversion in Matlab. It's just much easier, and it's quite a simple conversion anyway. So at the moment, let's just accept the fact that these 20 bits will be, in fixed point. We will append a string of zeros to make it 32 bits, and we will do the conversion back down to those 20 bits and convert it back to decimal in Matlab. So that's good enough for now, but what's next in this design? Well, I've got this big module here, and what's happening with this this module, now I've called it parallel to series, but really it's series to parallel. And what's happening is we have this count coming in, and that count is synchronized to the start of packet of the FFT. So if we have a look, we have the output of the FFT called start of packet, and that's the first sample of the output of the FFT. And this count is synchronized to that start of packet. And the reason we do this is because we can actually put a number to each FFT output. And remember, we know that bin 10 carries the fundamental, and then bin 20 carries the first harmonic, 30 carries the second harmonic, and so on. So having a counter here, and it might be worth clicking into this. So this counter will reset itself when start of packet is equal to 1. So we know that the value of this count will correspond to the frequency bin that we're currently on. And the count is output from this module, and it goes into this big module here. Now let's have a look what's going on inside. So all we're doing at the moment with this parallel to series module, I'm actually suspicious of this. Let me just double click. Yeah, that one wasn't the correct. What's going on inside this module is we're using an if statement, and we're looking to see what the value of count is. If the value of count is 9, that means we're on bin number 10, because DC counts as 0. So count number 9 corresponds to bin number 10, which is where the fundamental frequency is. Now, as soon as that happens, we will register the value of data in at that point. So data in, I think, is the voltage. S data into is the current of the FFT output. And we will register the value at that moment in time into fundamental V and fundamental I. So that then will stay at the value of the fundamental frequency component, 50 Hertz, and that will just stay at that value because it's registered in at that moment in time, and then it just stays at that value. We do exactly the same thing for the harmonics. So we wait until count 19, and then we register the value of data in at that time, and S data in 2, that's the voltage and current. Remember, that's going to change because it's basically scrolling through all of the FFT output results. So bin number 10 is going to be the fundamental, bin number 20 is going to be the first harmonic, 29 is going to be the second harmonic, and so on. And that's why we go up so far here, because we actually go all the way up to the 700th, not the 700th harmonic, the harmonic which corresponds to 700 Hertz. So that's our basic strategy here. And then the output of that module is going to be sent to the embedded processor. So you can see we've got all these outputs here. So we've got the fundamental voltage and current, we've got all the harmonics, and we've also got the phase as well, which is calculated by the Codec algorithm. Those values will be sent all the way around here, and this is actually the embedded processor. You can see all those, sorry, this is the interface code for the embedded processor, but all of those values from our Power Analyser are now being input into the control logic for the embedded processor, and they will eventually make their way into the memory scope of the embedded processor. But the big question now, and this is quite a big challenge actually, how do we write data into the memory scope of an embedded processor? Okay, because we need all this information to be accessible to the embedded processor so it can printf that data over the UART and into our graphical user interface. Now, just to go forward a few steps, this is the code I'm using to do exactly this job. And you can see what we're doing is using the printf command, and then we're using this IO read. That's just reading a portion of memory. Okay, this is the on-chip memory to base address, and this is the offset. So you can see we're offsetting by different amounts for each printf. So each offset will carry or will contain a different segment of information, whether it's the fundamental, the harmonics, or the phase. And this basic C++ code is just printfing all of the different offsets, and that's all our information going to the Matlab graphical user interface. So that's a few steps forward, but what we need to resolve now is how do we get that information into this memory scope? And it's worth spending a bit of time on this because it is quite a big challenge. But first, let's address the question of how we actually make an embedded processor on an FPGA. Well, an embedded processor is simply using the logic elements to perform the function of a processor. It's quite remarkable when you think about it how this is possible. Now, the number of logic elements necessary is around 3,000 logic elements for a basic embedded processor. But as soon as you have this, it allows you to run C and C++ code, which is a huge advantage because this gives you something that the basic hardware in the FPGA can't give you. But we got a problem now. We need to find out a way of communicating with the embedded processor. And one way we can do this is to use a write master. So a write master is it's a piece of IP which is produced by Intel. So you have to embed it into your embedded processor, and then you can actually write information into the memory scope of the embedded processor from outside, so from within our Verilog code, and we can actually target a particular base address within the embedded processor. There's a couple of little things you have to get right to get this working, but it's relatively straightforward. Of course, our processor is made up of peripherals, so the Nios processor core itself, of course. We've got a UART for sending information out. We also have on-chip memory. Now we know a portion of this on-chip memory will be used for the program itself, but you can offload this into SD-RAM if you want, and there is an SD-RAM chip on the Cyclone 5 board. But my design is all on-chip memory, so we have to be a bit careful that the memory address that we write to is well away from where that program is stored. Take a look at what happens when we use the write master. Now you can actually tell it to write to a specific address on the on-chip memory. Okay, so both the write master, that's us and our Verilog code, and the Nios processor know the base address of the on-chip memory. So we can actually write to a specific address, and then as we've already seen, it's quite trivial then to use the printf command. That's the easiest and most basic command we have in software, to actually send the contents of those memory addresses over the UART. So now it just becomes a question of targeting the right addresses. And if we get everything right, we can make this work. Okay, so this is my write master logic. So inside this block is some Verilog code for basically interfacing to the write master, and that write master is set up as a peripheral inside my embedded processor. So let's take a look inside the embedded processor. So I'll open up the QSys file, and this will open up the embedded processor. And it's not a complex design. There's only a few peripherals in here actually. So this is my embedded processor. So let's take a look at what we have. Right, okay, so this is the Nios processor itself. So fairly standard. We've got the UART here. So let's take a look. We can see we're running at a baud rate of 115.2 kilobits per second. We've got the on-chip memory here, and I've set this to a memory depth of 262 kilobytes, which is sufficient. This is quite large, so that's quite a significant portion of the capability of the FPGA we're using. And as I said before, if we start to run out there, we can actually move to SD-RAM. So there is another option there if we do run out of memory. But for simple designs like this, I think using the on-chip memory is probably okay. Then we got the master template. So again, very simple to set up. We've just set this up as a write master, 32-bit data width, 32-bit address width, and that's all there is to it really. There's not actually that much more to set up. Now one sort of nuanced point here, we have this PIO peripheral here, and it captures the falling edge of the input, and we can actually use this within our software to basically detect when something happens. So when we get to the software code, just make a mental note of checking what this corresponds to, because that's quite important, because we want our software to do something at a specific time. And I can actually show you in the code here that PIO flag is this one here, and that's coming in from this variable called control go. So basically every time we have a burst of data to write into the memory scope of the embedded processor, we will make this control go basically a one clock cycle flag to tell the software that we have something, do something basically. So that's the embedded processor. Not much to it really. Let's now move on to addressing this interface code. So let's take a look inside this write logic. So again, it's another fairly large Verilog module here, but the important stuff is in this always block. And you can see this always block, this code will be executed when the count reaches a particular value, and that value is stored in temp. So quite arbitrary actually. So I think about once every half a second I will sort of input the next round of data into the embedded processor. So that's why that's there. Now to make the write happen, what we need to do is first of all make sure we address the correct base. So we do have to make sure that this base address here matches the on-chip memory. So that has to be within the scope of the range of memory which makes up the on-chip memory. Then we have the control write length. So this is the number, that's the number of bytes that we intend to send. So in this case we're sending 120 bytes in that burst. Then we have user buffer input. Now this is actually the data that we want to send. You can see that comes out here. It's a 32-bit number, and that actually carries the data that we want to send. Now the first data I send, I've called it stamp. And stamp is one of the inputs that comes into the block. You can see stamp, stamp 2, stamp 3, all the way down to stamp 28. And each one of these carries with it one of the bits, segments of information we want to send. So the fundamental voltage and current, the harmonics, the phase, and so on. So that's the first 32-bit number we will send, and that will be written at this base address. Now the next data that we send is stamp 2. So the next clock cycle, user buffer input will take on the value of stamp 2. And this will actually write at an offset of 4 bytes. So it won't write at this base address. It will be base address, I guess, B0004. So there's an automatic offset. Because we're writing a burst of data, it will automatically offset by 4 bytes so it can store the 32 bits number that we want to send each time. And this process continues all the way down here until we've sent 120 bytes, and then the process finishes. Okay, so hopefully by time this finishes, we've written all the information we want to within the scope of the embedded processor. And then if we look at the code, we can actually execute this code when the PIO one clock cycle flag happens. It will then go about sending this information over the UART one at a time. Okay, and this is the on-chip memory base. Notice how that matches what we have in the Verilog code, OXB0000. And you can see, if you go back a minute or so, you'll see that that's the base address that we target. And then we use this IO read command, and that looks at the base address and the offset, and then it will printf that number over the UART into our graphical user interface. So I hope that makes sense. Now that there are a few more elements really to get right, to make this write master work, but that's basically what it is in a nutshell. So I think the next step now is to have a look at the graphical user interface in Matlab. Before I do that though, just one more point. We've got the UART transmit pin here, and that's going to this pin and this pin. So it's actually going to 2 pins. One of these pins is associated with the serial connector on the Cyclone 5 board, and one of them is just a pin. So what I've done is I've connected a USB cable from the USB port on the Cyclone 5 starter kit, and that's going into my laptop, and that that's what the Matlab graphical user interface will connect to, and hopefully pick off those UART characters as they come in and then plot it in a graphical user interface. Okay, so here I am. I'm using the app designer in Matlab, and this is the new version of a Guide. So some of you might be familiar with Guide, but this is the new way to make apps in Matlab. And I have to say, I'm not an expert by any stretch of the imagination making apps using Guide. But as you can see, I do have something up and running, and this is my graphical user interface. And you can see I've got a real-time plot of the power factor angle. I have a plot of voltage and current. I also have a dashboard here, which is plotting the voltage and, well, not plotting, but just listing the number of the voltage and the current and the phase. That phase should correspond to the same number in this graph here. And then also the complex power and the power factor. Now, I haven't quite worked out the scaling factors yet, because I've got a global scaling factor to try to bring it back to whatever the A to D converter is actually measuring. Now, that will actually depend on the sensor and the transducer that you use, so I've left that open for now. All I'm interested in now is whether it goes up and down, when the voltage and current goes up and down, and crucially, is it measuring the phase properly? So let's run this. I'm going to hit run. Right, now one thing I have to remember to do to make this work is, first of all, make sure everything is programmed, the device is programmed, so the SOF file has been sent. And then I just have to make sure the code here is running on the embedded processor. So, yep. Just made some cosmetic changes to that code previously. That should be up and running, and then we can open serial, and you can see we've got something. So what I'm doing is I'm sending 50 Hertz voltage and current. The amplitude for each of them is 400 millivolts. So the amplitude should be the same. I'm not sure why that's a bit different. But what I'm going to do is just change the phase. I'm going to make the phase go up by 1 degree. And you can see the phase difference has changed. Do another 1 degree. There we go. So it's quite responsive. And I'm quite impressed actually by how stable this is. Because the phase doesn't bounce around very much. Now I'm going to move if I go to amplitude, I'm just going to gradually increase the amplitude of one of them. I'll bring that back down again, maybe a bit of a lower resolution there, but it's definitely going up and down. I'm going to change the channel and make the other one go up, and you can see it's definitely responding. Now, what I'm going to try to do now, just to prove to you that the harmonics are working, I'm going to go to frequency, and I'm going to change the frequency to 100 Hertz. I was on the wrong channel. Let's just try that again. So 100 Hertz, and you can see we're now measuring 100 Hertz. And I'm going to just go to 150 Hertz. There we go. 200 Hertz. Now I'm only going up to 450 Hertz at the moment, but it is capable of going up to 700 Hertz at the moment, and it is possible actually to go much higher than this if we went back to the A to D converter and we increase the sampling rate, because at the moment it's on 10 kilohertz. We can get that all the way up to maybe 100, 200 kilohertz. And we could go significantly higher with the harmonics. Now, just to prove to you that it can measure different frequencies at the same time, big advantage of the FFT based system, I'm going to change it to a square wave. And of course, the FFT of a square wave is exactly what we see here. So it's measuring those harmonics all at the same time. And that's exactly what we wanted. So I'm quite pleased with this. I'm just going to go back to sine. The phase should stabilize now. They're both at 50 Hertz again. Let me just change the other one back to 50 Hertz. So the phase should stabilize now. So the phase minus 142.5 is very stable. I mean, this is quite an accurate system, but I haven't really tested it against any benchmarks yet. I guess that would be the next step. But I guess that finishes this this project. Very pleased with the way this has gone. It seems to be working fairly well. Now I will make this code available. I'll put the archived Quartus project in an accessible place, and I'll also list the code as well somewhere on the web so you can see the code for all of the Verilog modules. But I think I'll finish this video here. I've been talking too long and I hope you found that useful, and I'll see you next time.